In Lecture 4 of our Organic Chemistry lecture series, we're going to go over organic reactions and how to interpret what you're seeing. For starters, let's go into a couple acid-base definitions. The first definition we're going to go into is what constitutes a Lewis acid. A Lewis acid, quite simply, is an electron acceptor. The Lewis base, a donor. Bronsted-Lowry acids donate protons, and Bronsted-Lowry bases accept protons. Acids accept electrons, donate protons. Bases donate electrons and accept protons. However you keep these straight is up to you, but just make sure you know these distinctions. These definitions in particular will be tested. Acid-base strength. This all revolves around the acid dissociation constant, Ka, which is an expression of equilibrium. If you need a recap on equilibrium, look up your general chemistry lecture series. The expression for Ka is listed below, along with pKa and how it references Ka. The base dissociation constant, or known as Kb, can be calculated in much the same way, but the equilibrium expression is reversed. Also note that Ka times Kb has to equal Kw, or the equilibrium expression for water. And Kw, as a value, is represented by 1 times 10 to the negative 14. You'll notice that this 14 is where we get the pH scale from. Note that a higher Ka or a lower pKa signify a stronger acid, and the same applies for Kb. Here's a list of commonly tested acidic and basic functional groups. Make sure you have a good handle on these and what they look like. Their reactivities and how they react are going to be tested. Now that we've gone over acids and bases, let's go into some more organic chemistry specific reactions, starting with nucleophiles. Nucleophiles are called that because they are nucleus loving. Nucleo, nucleus, and phile, loving. They have lone pairs or pi bonds that form bonds with electrophiles. Because of these lone pairs, they tend to be good bases. Note that the solvent in which the nucleophile is immersed in is going to have some effect on its performance. Polar protic solvents will increase the nucleophilicity going down the periodic table, whereas polar aprotic solvents will increase going up. Make sure you're cognizant of the solvent. It is going to impact the reaction. Here are some factors that affect the strength of a nucleophile, starting first with charge. As you would suggest from a nucleus-loving entity, its strength is going to increase as the negativity increases. The electronegativity will cause the strength to decrease as electronegativity increases. And steric hindrance. Steric hindrance is basically how bulky the molecule is. If it's too bulky, it's going to have a hard time getting to where it needs to, thus decreasing the strength. And lastly, we mentioned this earlier, but solvents. Obviously, protic solvents will inhibit nucleophiles because the protons are going to get in and affect the lone pairs. We've talked about nucleophiles, so how about we talk about their counterparts, electrophiles. Electrophiles, as the name suggests, are electron-loving. They have a positive charge on a positively polarized atom, which is the way they accept electrons. They generally act as Lewis acids in reactions because of this reason. Nucleophilic substitution reactions. These are the reactions that you will most likely see on the MCAT. The SN1 reaction is a unimolecular substitution, and it involves two steps. One is a leaving group ejection, and followed by a subsequent nucleophilic attack. The leaving group is ejected, which is the rate-limiting step, and a carbocation is left. The nucleophile then attacks and forms a new compound. Since there is a two-step reaction, the leftover and the structure that comes from the attack is going to vary. This will produce a racemic mixture. The other type of reaction is an SN2 reaction. This is a bimolecular substitution, and it is only one step, called a backside attack by organic chemists. This requires a strong nucleophile and a sterically unhindered substrate. This will invert the structure and result in only one product isomer. Think of this as an umbrella. The general attack for this is going to be on a ketone or an aldehyde of some sort. But you may see other types of SN2s on the test. Note that there are also E1 and E2 reactions, or eliminations. E1 is similar to an SN1 reaction, but instead of a nucleophile attack, it simply eliminates the leaving group and bonds to itself to close off. An E2 is very similar, however, this happens in one fell swoop, or a single step. Take note that an SN2 reaction is going to favor sterically unhindered substrates, so end groups, or parts at the end of molecules, are going to be more favorable than parts directly in the middle. For this little bit, we're going to go into some oxidation reduction reactions. Without going into too much depth, here are some oxidizing agents and reactions that you will commonly see on the MCAT, and these are some reactions that we will go over in the coming lectures. This is from a Kaplan test prep, and they were nice enough to list out a lot of common reactions and reagents. For oxidizing agents and reactions, there are also reducing agents and reactions. Below are some common ones that you will see on the MCAT. Note that lithium aluminum hydride and sodium borohydrate are going to be the two that you will likely see. Note that sodium borohydrate is a little bit milder than lithium aluminum hydride. For the last bit, we're going to talk about chemoselectivity and what it means. Chemoselectivity is quite simply the preferential reaction of one functional group in the presence of other functional groups. So, selective, selectivity, chemoselectivity. Here are some criteria to consider when you're looking at chemoselectivity. Reactive locations, where the reaction is occurring. Steric protection, how bulky the molecule is and what those groups are doing. Steric hindrance, also a measure of how bulky it is. And resonance, resonance being the passing of electrons and overall stabilization of the structure. There are also protecting or shielding groups and the environment. These two factors go hand in hand because the protecting and shielding groups sometimes are within the environment, which in the case of chemistry is largely based on the solvent. Now that we've covered some general reaction mechanisms, let's go into how to approach a problem. First and foremost, you have to look at the starting molecule and the ending product, and you have to assign the proper nomenclature. Next, you have to identify potential participating functional groups. So, on the start and the end molecule, you need to look and see which functional groups there are, and which ones have changed, and which ones are likely to have had some participation in the reactions. Next, you have to identify any other reagents. This is to signify what effects they'll have. And you have to identify the most reactive functional group, because this is the one that's likely going to react. Now that we've done the correct identifications and processings, we need to identify the first step of the reaction. And lastly, you have to consider stereoselectivity. I've found that with a lot of organic chemistry reactions, sometimes it helps to work backwards and try to visualize the steps. On the MCAT, you'll rarely see overly complicated syntheses. Most of them are very straightforward and simple, so you should be able to break them down into a step or two. Alright, so I know that was a lot of information, but when it comes time to take your MCAT, you need to have a good grasp of organic reactions and how to analyze them. For the next couple lectures in this series, we're going to go into some types of reactions and what type of functional groups will react with what. Please join us in the next lecture as we go over alcohols.